How's it going, everybody, and welcome back to our NSX-T series. In this video, I'm going to switch gears a little bit, and we're not going to be doing any deployment. I'm going to be pulling over a lot of the notes that I've got for NSX-T, and I'll be walking you through the control plane logic and some of the theoretical pieces to how NSX-T actually works. So let me go ahead and pull this over here. I will share out some of the stuff that I've taken notes on and stuff like that. There is some capabilities in here that we'll talk about that are specific to how VMware NSX-T, how it actually works and stuff like that. But I do this now versus doing it earlier in the series because of the fact of we've actually got something deployed and you've actually seen something. We've done some stuff. So you're not completely in the blue as to what something is going on. So I'm actually going to go ahead and zoom in on this so that it's easier for you guys to see. And I'm going to go ahead and get out of the way. So without any further ado, and I will share this out. It'll be basically just I'll convert this into a PDF that you guys can download. So at a high level review, NSX-V, there are still deployments of NSX-V that are out there that I am on a regular basis working to migrate away from to a T environment. So, V is managed using vCenter. T is decoupled, and you join vCenter as a compute manager, and then you can deploy NSX-T to the host and things like that. Now, unlike V, there's a lot of capabilities that T supports that V would not. But so, for example, you can do a lot of things in T that you can't do with V. So vCenter, or V was tied to vCenter. It was Vsphere only. T supports a lot of additional capabilities, so on and so forth. So, and what you can manage, so in V, you would do one NSX manager to one vCenter instance. If you had two vCenters, you needed two NSX managers, and you would combine them together. Where in T, you can have one manager managing multiple vCenters. You can add as many vCenters as it's supported per the version of, or the deployment mode you've done for NSX Manager. So there is an upper limit. I don't remember off the top of my head what it is. So, so the management control and data planes are also, we need to understand how that works as well. So you have a manager cluster. So by default, you're supposed to actually deploy 3 managers when you deploy it out into a cluster. And the idea is that you deploy 3 managers into a management cluster. It doesn't have to be a management cluster. It can be a cluster of ESXi hosts that isn't tied to management or doesn't have the management nomenclature. I've deployed 3 NSX managers into the workload domain and been just fine. The key factor, though, is when you are doing any type of NSX capabilities for NSX manager deployments, I should say, you're going to want to use Affinity Groups. So let me take a moment here and explain what that means. Affinity is a variable, and you have a way of pairing things together, meaning you can either tell NSX or tell vCenter server to say, hey, if you have more than one light device. So for example, I've got 3 NSX managers. The only difference between those two is the name and the IP address. Everything else about them is the same. But you don't want them to sit on the same ESXi host at the same time. So you want to spread them amongst a group of servers. Maybe you have 3 hosts that are in your management cluster. And for the sake of argument, we're just going to say management cluster because it's easy for reference. So you have a management cluster. You deploy your 3 NSX managers to the management cluster. You would then create a affinity group that would be a host to VM binding. And what you would say is do not let the 2 NSX-T managers reside on the same host at the same time. It's what they refer to as an anti-affinity group. So if you do not want NSX managers, or if you don't want virtual machines in general, if you don't want specific virtual machines to sit on the same host at the same time, you would create an anti-affinity group, and then you would put the specific logic in there and how that would come into play. I'm actually going to show you how to do that when we deploy the edge nodes, because the edge nodes will have the ability of doing vMotion through the management network, but the key factor is we're going to set it up to where we're not going to allow the two edge nodes to sit on the same host at the same time. They will not be able to be co-located on the same host. And that's going to be for redundancy, right? We don't want to accidentally have a physical host crash, and then you end up having all of your connectivity go down because of a device, a virtual machine goes down with the host, right? You know how they say the captain goes down with the ship. Well, the manager, the edge node, whatever it might be, you don't want them all co-located on the same physical hardware in the event that there's a hardware failure. Power goes out, network connectivity is lost, whatever the case might be, you don't want that to happen. So you're going to try to stretch it across as many hosts as you can in order to get the job done. So that's one thing I wanted to point out. So the configuration changes are synced across all nodes in the cluster. We only have a single node deployed, which is completely fine. It definitely works. But in a real world deployment, you're going to want to deploy at least 3 nodes. And then you're going to create a virtual IP address or a VIP that one of the managers will take control of and respond to communications and things like that. So the control plane is hosted and operated by the management cluster. So anytime you make any changes to logical switching, logical routing, or distributed firewall, all of those changes are handled by the manager, and then that information is synced between all of the managers themselves. And I'll talk a little bit more about how that works here in just a second. Any changes by the manager are pushed down to the logical constructs. So VMNIC mappings to logical switches, associated logical switches to distributed routers, routing operations on distributed routers, firewall rules on the distributed and edge firewalls. We will be taking a look, and my intention is to do layer 2 networking first, then layer 3 routing, and then talk about how all that works, then do firewalling on distributed firewall, then do edge firewall, and that should get the majority of what we need to do under control and have all that stuff laid out. That is the flow that I'm looking at doing for this series, but there's a lot of individual things we're going to be doing in addition to that. So we'll take a look at those things in more detail when we get there, but that's essentially the direction I want to go. So the capabilities that we're talking about here are things we're going to be actually seeing. Now, the policy manager is intent-based management, which is how we're actually going to be managing, is going to be via the policy version of NSX Manager. There's a policy and there's a manager. And so what's interesting is the policy view of the manager and the manager view of the manager have 2 different UIs. The policy is going to be what you see, what you've seen so far, where you have networking, you have segments, so on and so forth. Where the manager, you would have logical switches, which is what the switches were referred to in NSX-V. That was a logical switch. Distributed logical router, so on and so forth. So that's basically where that comes into play. Data plane, where the actual traffic flows. So this could be ESXi, KVM, or other supported platforms that are out there. You can also deploy NSX-T in Azure, AWS, VMC on AWS, and IBM. Now, there's a few things that we need to talk about when it comes down to how they come into play. So you have the policy role, the manager role, and the controller role. Distributed replicated database. So what's going to end up happening is you're going to have changes made on one manager are replicated to all the other managers on the stretched database that sits in between all the managers. There's a virtual IP address and all managers in the same subnet. Each manager has a dedicated IP for tracking purposes, all going to share the same IP address. That's the VIP. One manager will be elected as a leader. If a manager fails, fail over to another available manager. You're going to GARP from new manager for network updates, which is a gratuitous to ARP. Essentially, it's going to go to the network, the network adapter, and just say, hey, this is my updated information. If load balancing is needed, each manager can be placed in different subnets. So if load balancer can be the NSX-T load balancer or AVI, or third party. So it doesn't really matter which one you use. Becomes active-active workflow. On the controller concepts, function of the NSX manager, not a separate appliance. So again, logical switching, logical routing, distributed firewall are all handled by the controller portion of NSX-T. Now, let me be clear here. In NSX-V, the way that you would do things is you would deploy your NSX manager, and then you would go and deploy controller VMs to your ESXi environment. So you'd have a dedicated virtual machine that would get pushed by NSX-V to some host in your ESXi environment, and you would then be able to start interacting with logical switching, logical routing, firewall, etc. Now, in NSX Manager, the controller VM is no longer a concept. The controller is not a separate entity. It's built into the manager out of the gate. So your job to deploy manager, you're going to be deploying the controller at the same time. So the NSX Manager centralized control plane to transport nodes. So you have the ESXi host has an LCP. The LCP is local control plane and it exists on every transport node. An ESXi host is a transport node. It's providing the transport. NSX-T is providing the network transport for whatever VMs are attached to NSX-T logical capabilities, whether it's in a VLAN back segment or an overlay segment. CCP is Central Control Plane Cluster, ran on the NSX Manager. So for Layer 2 switch, L3 routing, and firewall control plane operations, if a VM vMotion is between transport nodes, the LCP, the local control plane of each host, will update the CCP, the centralized control plane, and keeps the tables updated. What does that exactly mean with the tables? So there's going to be a number of tables that are going to be used to keep track of where VMs are sitting in the network. Because what I want you to think of this is, let me go ahead and pull up a diagram real quick. What's going to end up happening is you're going to have a control plane connection from NSX Manager to each one of your ESXi hosts, right? And so far, this is as far as we've gotten. We've deployed NVDSs, we've done uplink profiles, transport node profiles, all that good stuff. So we have just a basic deployment of NSX-T deployed. What's going to end up happening now is there are tables, logical tables, that have been installed on every one of these hosts that are going to keep track of VM network adapter to logical switch port mappings that we're going to be doing, or segment port mappings. And that information is going to be updated at the host level, and then it's going to be propagated to NSX Manager. When that happens, if I vMotion, let's say you have an environment that is dynamic and you've got a lot of VMs being vMotion back and forth. If you were to put a microscope or a spyglass right where my mouse is over this control plane line, you would see a lot of communication going back and forth on each one of these dotted lines from every one of the hosts. Whenever a virtual machine moves, it's going to move from one host to the other. And the reason why that needs to be updated is because essentially what will end up happening is you've got a stretch. The segments that we're going to be creating and pushing down to these hosts are stretched across all four hosts. So think of the segments we're going to be deploying as one big switch. And you're going to have a VLAN or one big VLAN that's stretched across all four hosts. No different really than how a virtual distributed switch, right? So if I have communication going back and forth between these hosts, and I have VMs moving back and forth between a couple of hosts, in order for if a VM1 on DC1 moves to VM or DC ESXi2, I need to make sure that the rest of the network knows if you need to reach VM1, you need to point to ESXi2, not ESXi1. And that's where that updating comes into play. So the local control plane gets it, vCenter moves the VM, and then through a vMotion for whatever reason, and then LCP gets updated, then ALCP sends an update to NSX Manager. NSX Manager gets the update, pushes that information down to the other hosts so that they know where to go. So that's one of the key things that you'll need to remember is that you're talking software-defined networking. You're not each one of the hosts is still has a level of individual configuration, but once you have all that communication in place, you need some way to make sure that it's referenced elsewhere. Because especially when we get into overlay networking, that's going to become even more specific because the physical network isn't going to know where it's at. VLAN back segments are not that big of a deal because of the fact that you're still using the communication across the wire to do that. You're just changing how the port group is allocated. You're deploying a NSX-T port group versus a VDS port group, and when you do that, that really just changes how ESXi does its networking. So then the VM gets mapped to an NSX port group and then forwards traffic on. So the physical network is still going to know where your virtual machines sit based off of where the communication is coming from. It's still going to look like it's coming from a host because it is a host. It's just how the networking is set up is different. Where in overlay, it's different because the physical network isn't going to know anything about that. So that's even why it's more imperative for the control plane that is being learned back and forth between all these devices is as accurate as possible, because you don't want to accidentally lose connectivity to a virtual machine while it's peak operating procedures. Okay, now that I've covered that, there's this concept of control plane sharding. So 3 controllers running, 1 on each NSX manager. Each transport node will be controlled by one of the controllers. If a failure occurs, no data loss occurs since the databases are replicated. The transport node LCP, local control plane, and the controller central control plane connection is severed. Those transport nodes are distributed to other controllers. In other words, when you have you got your 3-node management cluster deployed, and let's say you have 9 NSX enabled ESXi hosts. You're going to send 3 of those hosts are going to be connected to manager 1. The next 3 are going to be connected to controller 2, and then the last 3 hosts are going to be connected to NSX manager 3. This way here, if there's a connection error on any one of those devices, the host that's hosting NSX manager 2 goes down. Well, the 3 control plane connections that NSX manager 2 had to host 4, 5, and 6 are going to have to get moved to NSX Manager 1 and 3. And that's where that concept comes into play of being able to distribute your workload. You are not tying all of your control plane connectivity to a single device. That's actually not a good idea. So it distributes the control plane across all of the managers so that you don't have everybody tied to everybody else. For the data plane, it forwards the traffic, also referred to as the data plane. It runs on hypervisors, bare metal servers, the NSX edge. Now the transport node, we talked briefly about that. The transport zone is going to dictate which hosts can participate in NSX. That's literally exactly what it is. It's a boundary point. Then you have the NVDS, which is, there's 2 different versions of it. You have the NVDS that needs to get pushed when from NSX Manager. So it's going to be a dedicated switch that is added to the ESXi host that's going to handle NSX traffic. Then you have the TEP, the tunnel endpoint. This is going to be for Geneve encapsulation termination. So you're going to have a couple of hosts that are going to be participating in overlay networking, and the TEP IP address, the tunnel endpoint, which is what TEP stands for, you're going to want that communication to be going back and forth between the hosts. So you're going to have a dedicated VM kernel adapter that you're going to be sending and receiving traffic from, and any traffic that is going to be overlay VM NICs that are attached to overlay segments are going to be using the tunnel endpoint, or the TEP, as its ingress or egress point or to the overlay connection that we're going to be setting up. The VIB, or VMware installation bundles, deploy the NVDS, the LCP, communication between the ESXi host and the NSX manager, MPA, the management plane agent, which retrieves status of the firewall and other stats, and then edge connections to external networks, which are going to be VLAN back segments. So this right here, this connectivity, that it's not visible here in this topology. Here, let me pull up the other one. Let me do... Actually... No, sorry, not this one. What's going to eventually end up happening, and I'm jumping ahead a little bit, is we're going to, this blue line that you see right here, and this green line that you see right here, they are each going to go connect to a specific CSR 1000V, and we're going to be connecting the edge node to the upstream connection, the upstream CSR 1000Vs, So that's going to how physical to virtual networking is going to end up happening. I'll come back to that more in detail later, but that's essentially what we're going to be doing. So that's where that external connections to external networks. Now, when it comes to the architecture, NSX-T can be deployed any site, data center, DR site branch, any cloud, public VMware, NSX, any device, VM, bare metal container. The real big benefit that we get from it is its policy and consistency. It allows policy definition once and realizable end state via RESTful APIs, addressing requirements of today's automated environments. NSX maintains unique and multiple inventories and controls to enumerate desired outcomes across diverse domains. Networking and connectivity allows consistent logical switching and distributed routing with multiple Vsphere and KVM nodes without being tied to a compute manager domain. Connectivity is further extended across containers and clouds via domain-specific implementations while still providing connectivity across heterogeneous endpoints. That is basically just a lot of architecture speak for if I have a scenario where I need to have connectivity from my on-prem data center to a cloud presence, I can do that. And I can allow that communication to happen back and forth all day long. And I can keep the networking in lockstep, meaning that whatever I deploy here is going to also show up over there, and I can maintain my firewalling end to end. I can maintain my security presence no matter where I'm at. When it comes to security and services, allows a unified security policy model with networking connectivity. This enables implementation of services such as load balancing, edge gateway, distributed firewall, and NAT across multiple compute domains. Providing consistent security between VMs and container workloads is essential to assuring the integrity of the overall framework set forth by security operations. In other words, again, more architecture jargon, I want to make sure that no matter where I have workloads sitting, that if they are a virtual machine or container sitting on-prem or in the cloud, I can control what's going on with them at all times. I'm not guessing that I've got the firewall rule built right on this firewall and that firewall. When I deploy it to this guy, it's distributed across the entire environment when I'm dealing with DFW. That's the key thing here. Now, when it comes to visibility, allows consistent monitoring, metric collection, and flow tracing via common tool set across multiple compute domains. Visibility is essentially for operationalizing mixed workloads, VM and container centric. Typically, both have drastically different tools for completing similar tasks. Having visibility on what the network is doing is pretty important. And this is going to be just another tool in your tool bag that you're going to be able to leverage in order to get the job done. So we're going to talk more about that in detail when we get into how everything comes into play. But let me go ahead and wrap this video up by covering some of the capabilities that NSX-T provides. So policy-driven config offers automation by using the REST API that allows simplified policy-driven configuration so admins can simplify the design of configurable items. So it gives you a lot of flexibility. You can leverage automation tools to do the job that you need to do. One of the things that I've used a few times is a thing known as Postman, where you can literally script things using a spreadsheet. Like if you have a CSV file and you want to take a bunch of information, like you got a bunch of segments that you want to create and a bunch of routing that you have to go do, guess what you can go do? You can literally populate a spreadsheet, and the spreadsheet can be formatted a certain way, and you can call that from Postman, and Postman can push those configs via API. Now, Vsphere Cloud Foundation, or VCF, uses a similar capability. When you deploy the SDDC manager, you have a spreadsheet that you have to populate, and it will literally go and deploy everything for you. That is something that I'm going to be working on here in the near future and do some demonstrations on how that actually works. Hypervisor support, you can deploy on ESXi and KVM Type 1 hypervisor. Bare metal support, so you can do bare metal running on Red Hat, Linux, Windows, and other OSs. Support for VMs and containers. Supports networking and security services on VMs and container workloads. That's kind of a big deal right there because I know a lot of customers that are using things like Kubernetes and being able to take advantage of vSphere networking, or I should say NSX networking for that is a big deal. And NSX, AWS, and Azure instances. Now, NSX Cloud supports networking and security for your applications running natively in public clouds. That's a big thing. vCenter server agnostic. You can set up multiple vCenter servers as endpoint managers and allow multiple hosts and multiple clusters spread across multiple vCenters to be host transport nodes. I think that when I talk to customers and we're actually doing that, that's a huge benefit. I can deploy a cluster of 3 NSX managers and I can connect 20 different vCenter instances, and I can have as many transport node and uplink profiles as I need to in order to get the job done. That's a really, really powerful thing. It is HTML5 UI, and then we have the DPDK, or the Data Plane Development Kit, and based NSX Edge nodes or bare metal form factor. So DPDK, Data Plane Development Kit, collects data plane libraries and NIC controller drivers that offer fast packet processing capabilities, where it optimizes the CPU and memory to allow packet processing speed. This is automatically enabled. We don't have to do anything. It's automatically there. Multi-site and federation offers stretched network and security services across multiple sites. Simplifies the DR across various locations and allows you to offer unified network and security services across multiple sites. Let me pause right there for a moment. Multi-site and federation are 2 different DR sites to deploy with. So, multi-site is going to give you more flexibility. It's going to have more services, more capabilities. Federation is more of a hierarchical way of doing things, where multi-site, I'm just going to add another vCenter or another data center, and I'm going to allow that manager to manage another data center. And multi-site gives you more flexibility. It's got more capabilities. Federations, you are going to have a global manager, which is going to be in charge of everything. Then you're going to have local managers at each site. And local managers are going to, for the most part, inherit all their configurations from the global manager. So, and then the local manager will handle the local control plane per site. Global manager has visibility into everything. I'm going to be walking through how federations work. It's more of a complicated design, but you lose a lot of feature capabilities in federations that you don't lose in multi-site. So depending on what your needs are will determine which version of multi-NSX deployment you go. I prefer multi-site. It gives me more bang for my buck. However, federations sometimes are easier to work with because they give you a hierarchy where multi-site does not. It's NSX managers manage multiple data centers. So at the end of the day, it's not that terrible to work with, but if you're on the fence on that type of stuff, I can understand. So that is the overview of NSX-T. I'm gonna go in the next video, go over some of the features of what we can do, and then we're gonna start diving into how we can actually deliver those capabilities and stuff like that. So until next time, guys, thank you so much for stopping by and hanging out with me in this video. If you have any questions, please leave a comment in the comment section below. If you haven't already done so, please like, share, and subscribe, and I'll catch all of you guys in the next video.